All right, so the lab that I passed out the other day, the one that you're working on, you're going to make Pascal's triangle, correct? And in that lab, you have to have two functions. What are the two functions? One of them is factorials, and the other one is, you might have called it many different things. You might have called it Pascal. You might have called it combination.
Why was Pascal blue? I call it Pascal's variable blue.
I didn't know that. I don't know why Pascal is blue.
Mine always turned blue.
I don't know why Pascal would be blue. It must be a command for something. I don't know what it does, though. All right. Anyway, in that, in your function, I probably would have called it combination. Within that function, you call the factorial, don't you? So this program is a good example of how you can call one function from another function. You're inside the combination function, but you call the factorial function and you use it. Today we're going to talk about something similar. We're going to talk about recursive functions. Anybody know what a recursive function is? It's a function that calls itself. So it's called recursive because the function recurs. The function starts, the function calls itself, it recurs, and then it keeps going. Maybe it calls itself again and again and again. Okay, so there are several classical examples of recursive functions, and we'll do a few of them today. The first classical example of a recursive function is factorial. I'm guessing from what I saw in the lab the other day that very few of you wrote the factorial function as a recursive function. My guess is you wrote it as a for loop, which is another classic way to do it. But today we're going to write it as a recursive function. So, if we're doing factorial, what kind of function will it be? What kind of variable will it return? Int. And we're going to call it factorial. Do we need to send it any variables? One. And what type variable? Int. And what are we going to call it that we send it? Num? All right. Copy and paste, and now I got to wait. Should have just typed it. It would have been quicker. Here's how this is going to work. We're going to have a little if statement. If num is less than or equal to 1, return, what's 1 factorial? 1. What's 0 factorial? Also 1. So if the number that we type in is less than or equal to 1, what do I want it to return? 1. It's easy enough. Otherwise, I'm going to return num times factorial num minus 1. So you can see right here, I'm calling the factorial function, which is the function I'm already in. So this function is calling itself. All right, so let's finish the main, and we'll run this, and we'll see that we get the right numbers, and then we'll talk about how is this really working and what's it doing. All right, what would I need up in the main? Directions. Enter a whole number, and I will give you the factorial. I heard we need to declare a variable. What variable do we need? We need an integer variable for the person to type in a number. So int number. Probably should go up above the directions, but we'll put it there. Tell the person to enter a number. See out. I guess I already said that, didn't I? Enter a whole number. So I guess I can just do Cn at this point. Number. And then I'm just going to do one more Cout. Cout. Number. Factorial. Equals. Factorial of the number the person typed in.
But if we do the if statement, then once the factorial gets down to 1, when it just return 1?
Yep, it will. It's okay, I think. Let's run it and see if it works. And then we'll get a piece of paper out and we'll talk about what it did and how it worked. Loading. Enter a whole number, and I will give you the factorial.
4, 3.
4, 3, because those are numbers we know 4 factorial is. We know what 3 factorial is. 4. 4 factorial is 24, is that correct?
Yep.
4 times 3 times 2 times 1 is 24. That's correct. All right, so what did this do? So when I sent 4 into this function, when I called factorial 4, when I called that within my Cout, what happened? 4 went into the function. Is 4 less than or equal to 1? No, 4 is not less than or equal to 1. So it returned num times factorial num minus 1. So it returned, what's num? 4 times factorial num minus 1. What's num minus 1? 3. But factorial 3 calls it again, doesn't it? So now it does, it's got the 4 here. It's going to do times, what does factorial 3 do? It returns 3 times factorial, it's hard to spell, 2. Then it has to run the factorial function again. What does factorial 2 do? The 4 times the 3 is already there. Factorial 2 is 2 times factorial 1. And finally, factorial 1 is? Now it hits the if statement if num is less than or equal to 1. This is less than or equal to 1, so it returns 1. And that's the answer you get in the end. It returns all those things one at a time. 4 times 3 times 2 times 1. So it's kind of like having a built-in for loop. It kind of starts at 4 and does 4 times 3 times 2 times 1. And the way it's doing it is right here, we're subtracting 1 each time. So first it spits out the 4, it subtracts 1, which is 3, and goes back. That spits out the 3, subtracts 1, that gives a 2, and it goes back. So on and so forth. So this recursion is in a sense like building a little for loop, and this little if statement is what tells the for loop when to stop. Stop when you get to 1. Questions on that? All right, so I just wrote part of your program for you. Of course, a lot of you have already finished it and turned it in, but if you haven't, here's the first function that you need. You need a function that does factorial. There's a function that does factorial for you. Yeah, like the very next program that you have to turn in. It's a good one right there. All right, the next classical example of recursive functions. Never remember how to spell this guy's name, so I got it written down here. are the Fibonacci numbers. Does anybody know what the Fibonacci numbers are?
1, 1, 2, 3, 5, 6.
All right. And anybody who doesn't know what the Fibonacci numbers are, look at that sequence and tell me what the next one should be. The next one should be 8. 13. All right, how are you getting the numbers? All right, so you start with 1 and 1, and then you add. 1 plus 1 gives 2. And then you go back. 1 plus 2 is 3. 2 plus 3, 3 plus 5, so on and so forth. 5 plus 8 is 13. 8 plus 13, the next one would be 21. The next one would be 34. And you could go forever and ever and ever as long as you want. Why are those numbers famous? Anybody know? They occur naturally in nature.
Which I guess is
Seems a little redundant, that's true. Where do they naturally apply in nature? Pine cones is a good example. If you look at a pine cone, it's got little flakes on it. If you look, there's one little flake right on the end, and then there'll be another little flake next to it, and then there'll be kind of a spiral of flakes, and as you go around the spiral, each trip around the spiral, you get the next Fibonacci number. Happens on pine cones. Happens on sunflowers. If you look at the seeds in the middle, there's one in the middle, one next to it, and then 2, then so on and so forth. And again, they spiral in the Fibonacci number, in the Fibonacci numbers.
Find a pine cone that's not like that. It's like a
Correct. They're unusual. They do happen, but they're unusual. A pineapple is another example. The little spikes on a pineapple follow spirals of the Fibonacci numbers. So, lots of good examples of Fibonacci numbers. All right, so what we're going to do is we're going to write a program that allows a person to put in a number like 7, and our program will compute the 7th Fibonacci number. So 1, 2, 3, 4, 5, 6, 7. If our program runs correctly, it should give us an answer of 13. All right. Oh, I should save this little program first, I guess. So I don't want that. And I guess I'll get rid of all of that. Alright, so in this program I think I'm going to want one function. What's my function called? And what kind of function, what kind of value does it return? An int. So int. We're going to call it fib because we can't spell Fibonacci. It's a good idea. Will this function have any inputs? Yes, the person's going to tell I want the 7th Fibonacci number, or I want the 12th Fibonacci number. So what kind of input does it take? Int. And what do we want to call that? Number. That's too long? Not too bad. Int. Fib. Int. Number. Alright, we'll come back to that and we'll write that in just a minute. What's going to happen in our main? And I will compute. So directions, see out, enter a counting number, and I will give you the And I will give you, you know what, I'm going to give all Fibonacci numbers up to that number. All Fibonacci numbers. My wording stinks. Up to the value. It still stinks, but we'll live with it. We know what we mean. Well, it does. I mean, if you give bad directions, then the person's going to enter bad data. So, good directions are very important. But those directions stink. But we'll live with them. All right, what else do we need? A variable. What kind of variable? Int. Num. See in the num? So what I'm thinking is, I want to actually give them the whole list of Fibonacci numbers. So I want it to, if they put in 7, I want it to go 1, 1, 2, 3, 5, 8, 13. Did we decide 13? So I want it to get that whole list, not just say the 7th Fibonacci number is 13. I want to get that whole list. So how are we going to get that whole list? The way I'm thinking of doing the function, that won't work. Yeah, I was thinking I would just do a for loop, and if they give me the number 7, I would send 1 to the Fibonacci number, and it would give me an answer. Then the for loop would say send 2 to the Fibonacci, so on and so forth. So that's what I was thinking. So that's what I'm going to do. For int count equals 1, count less than or equal to num, count plus plus. See out, fib count, and I'll just put a couple spaces in between so the numbers are spread out a little bit. So that's what I was thinking. I was just thinking I would do a little for loop, which would print the first Fibonacci number, the second Fibonacci number, the third one, so on and so forth. All right. Now, what goes in our function? The variable plus itself? Not quite. How do those Fibonacci numbers work again? I have to know 2 of them, don't I? So I have to know the previous 2. I also, kind of like in my factorial function, I need an if statement to tell me when I'm done and to not keep recurring. So I think that's where I want to start. So how do I tell this when to end? So well, it'll be count will become the same value as number. So in the function, I'm going to use number, not count. But when is this going to die? When's it going to stop recurring? I don't need a new variable. All right, here's what I would do. If number equals 1, what if I tell it I want the first Fibonacci number? It's just the number 1, isn't it? Or what if I tell it I want the second Fibonacci number? It's also 1. So if fib equals 1, or I'm sorry, not fib, number, or number equals 2, return 1. Because I know the first Fibonacci number is always 1, the second Fibonacci number is always 2. Now, how would I tell the computer find the third Fibonacci number. Add the first Fibonacci number plus the second Fibonacci number. Okay? So how do I code that? If I want to find the close, so very close, -2. If I want to find the 10th Fibonacci number, what do I need to know? 8 and 9, and what would I do to find 10? I would take 8, the 8th one and the 9th one, and I would add them together, wouldn't I? So we're going to have return fib of number -2. I had fib. I lied. Fib. Plus fib of number -1. All right, so again, let's take a second and chase this down and see what it's actually doing. So let's say I send, I guess I made this piece of paper. We're going to show the room on that one. What if I were to send fib 5? Well, what's fib 5 going to do? If I send 5 into this function, is 5 equal to 1? No, 5 is not equal to 1. Is 5 equal to 2? No, so it's going to come down here and it's going to return fib of 3 plus fib of 4. So this is going to return fib 3 plus fib 4. So now 3 is going to go into the function. Is 3 equal to 1 or is 3 equal to 2? No, so what's that going to do? All right, so this is going to return fib 1 plus fib 2. And then what's this part going to return? Fib 2 plus fib 3. All right, well, we're getting close because fib 1 is 1 and fib 2 is plus. Here fib 2 is 1 and here fib 3 is, this one's going to return fib 2 plus fib 1, but fib 2 and fib 1 both happen to be 1. So in the end, this is going to return 1, 2, 3, 4, 5. Is 5 the 5th Fibonacci number? 1, 2, 3, 4, 5. Yes, it is.
So this just breaks it down to a bunch of ones.
Eventually, all this is doing is adding the right number of ones. That is correct. It breaks it down. What this does is it calculates how many ones do I need and adds them all up. What's fib 1000?
Yeah.
Pretty darn big. I don't know.
We're going to find out.
That's why we write a program. All right, let's see if it works. So we said, well, first we said we were going to try 7, right? Just to make sure our programs were running correctly. So the first 7 Fibonacci numbers are 1, 1, 2, 3, 5, 8, 13. So basically what this tells you here, this 13, this function had to call itself 13 times. It ended up with 13 ones and it added 1 plus 1 plus 1 13 times. Eventually what it did. All right, so you want to try a big number now? 100.
It's lagging, so what
It's
is
adding
that?
so many ones in that set. Eventually, it's going to say 0, right?
Eventually, it will max out the size of int, and it will start saying 0.
Well, that's right.
All right. So why is it running so slowly?
Because it's adding a bunch of ones. It's just added 165 million ones.
Right. Unfortunately, when this runs, it doesn't remember this number and that number and simply add them together. That's the way it should do it to find the next one, right? It's having to go all the way back to the beginning and start with 1 plus 1 plus 1 plus 1, all the way back, figure out how many ones it needs, and then adds them all up.
No, that's probably why. It's probably in the air now.
So the moral of the story is, while this works, it's pretty slow. And the bigger the number gets, the slower it's going to be.
We got another one.
We got another one. Let's see if we can. How
You
many?
do hitman usually gives you like how long it took the program.
Yeah, when it gets all done, it'll give you a time run usually.
I don't know if it'll fix.
It will. It depends on how long are we willing to stand here and stare at the little blinky cursor there.
We got 30.
Like watching peanuts.
We got more to do though.
Minimize
It's going to
it.
take a long time.
It's going to take a long time. But again, there's a spit out another one. What it's having to do, unfortunately, is go all the way back to the beginning each and every time. What would be much better would be if I had a way to save this number and save that number, and then tell it just add those two together. Then it would run very fast.
Where you like set, like what you set through the equation and it equals this like variable and variable then at the very end of it it's like variable plus something or variable you do something so that it adds on what.
Right. The way to really do it is to store all these numbers as you go using something called an array. And that's what we will talk about when we come back from Thanksgiving. We'll get into arrays. And we'll talk about a much faster way to build the Fibonacci numbers.
But do you do it where you store two variables and then every single time it increases by one, it would store the smallest value of the variable? Like just keep on rotating like that.
Right. You could write this without arrays by returning two variables each time and saving them, and then resending those two variables to the function. Yeah, this recursive function for finding the Fibonacci numbers is very inefficient. You could write much more efficient functions for finding these than this. And the way to do it would be to save these two numbers somehow, and then use these two numbers to find the next one quickly, rather than going all the way back to the beginning and having to add all the numbers up over and over and over and over and over again. Yeah, I've seen
Just
enough.
minimize it and see if it how long it gets in the class.
All right, we'll minimize it. We'll leave it running for now. All right, the last classic example that I'm going to talk about. There are many classic examples of recursive functions. Save this program too, I suppose. The last classic example that we're going to talk about today is computing interest. You're interested in that? Good. Calculating our interest. And the closer it gets to Christmas, the smaller it gets.
Yeah, truncated though. Word classic
You don't want to give them half
All right, so let's say we had $1,000. $1,000. And let's say we found some fool who was willing to pay us 12% interest, compounded monthly. Why is this person a fool? That's an incredible amount of interest at this point in life. If you take your money and invest it in the bank, what kind of interest are you going to get? Oh, it's better than that. As you'll see.
It goes up every.
Well, the 12% is your yearly interest rate,
So does that
but it's
mean-
compounded monthly, which means they pay you interest every month. Anyway, interest rates today are like 0.03%, 0.05% if you're putting your money in a bank. You're actually losing money by putting it in the bank because the consumer price index is higher, which means inflation is higher than the interest you can earn.
Yeah, inflation.
William?
Let's say you have a credit card rate of 15%. Let's say you owe $1,000 on it, you don't touch it, you don't subtract anything or add anything to it. And 1 year, you pay 50% of that $1,000.
No, it's worse than that. Because they charge you that 15% every single month. So you'll end up owing more than just an extra 15% of the $1,000. Because they're going to charge you interest the first month, then they're going to charge you interest on the interest the second month.
Every month you're going to pick up, the first month you're going to pick up $150, the next month you're going to pick up slightly more than $150.
Yeah, because they charge you interest on the interest if you don't pay it.
What about credit union?
What about a credit union? Their interest rates aren't any better at this point. They're slightly better, but they're still well below consumer price index.
Besides those compounded means that they be built on top.
Yes, that's what compound interest means. Interest built on interest. Was compounded continuously?
No, I said we should compound.
We should compound continue. Oh, we're not going to. All right, so what we're going to do in this program is we're going to build a little table. Month and balance. So in month 0, we'll have $1,000. After 1 month, the bank pays us some interest. How much money is going to be in the account after 1 month? $1,000 plus 1,000 times 0.12 over 12. They don't pay you 12% every month. The 12% is a yearly interest rate. So how much is that? 1,010? Because 0.12 divided by 12 is, that's why I picked 12% to make the math easy. 0.12 divided by 12 is 1. 1% of 1,000 is $10. So after 1 month, you earn $10. What happens after the second month?
We get 1,021.
Okay. You get 1,010 plus 1,010 times 0.12 over 12. But where did the 1,010 come from?
The last month.
It came from the last one, didn't it? So this is where you're starting to get your recursion. The 1,010 came from 1,000 plus 1,000 times 0.12 over 12. So that's this 1,010. And then you'd have this 1,010, which is 1,000 plus 1,000 times 0.12 over 12. And then this is multiplied by 0.12 over 12. So this is where your recursion's coming in. It starts to loop around itself. We compute the next number by using the previous number. Or, even better, you could say, this is what is this? This is balance at month 1 plus balance at month 1 times 0.12 over 12. And then how would you find the balance at month 3? So at month 3, it would be balance from month 2 plus balance from month 2 times 0.12 over 12. So this is where we're going to get our recursion. All right, so let's see if we can write that in a program. See out. How many months do you want to invest your money for? Again, a poorly worded sentence. I shouldn't end my sentence with the word for. Too bad, didn't I? Then I guess I need a variable for months. And we'll see in months. Alright, so there's a little bit that's going to be in the main, a little bit of directions, and give the person a chance to enter a value. I guess up here we're going to want to make a function that's going to return the balance. So what kind of value is that going to return?
Float.
A float or a double, definitely. You'll start to earn pennies after a while. Alright, so float. I'll call it balance. Do we need to send anything to it? What do we need to send? Well, the starting value is always going to be $1,000. We could make this more fancy, where we could let the person type in the starting balance. We could let the person type in the interest rate. And then how many months? Yeah, we could do all that in the interest of time. The only thing we're going to send is the number of months. So I guess I'll call that time. All right, and then the other thing I think I'm going to want in my main is just a table. So see out, is that width 10 maybe? Month. Is that width 10 again? Balance.
So you get it up fixed so that you have that.
Should I type the right thing first there? So you want everything to 2 decimal places?
Yeah.
All right. See out fixed. See out. Set precision. And then I think all we're going to have is a for loop. For int count, okay. Count will start at 0. Count will go less than or equal to the months the person typed in. Count plus plus. And then all it's going to do is the same as the cout statement, except it's going to have the variables instead of the words. So instead of month will be the variable count, and balance we'll call our function to figure that out. All right, so there's everything I think we need in our main. Again, main usually ends up being pretty short, so we're just going to give brief directions. We're going to input the month, table header, 2 decimal places, and then fill the table. All right, so float, balance, float. All right, so how do we figure out our balance? Again, I think if this is going to be a recursive function, we need to begin with something that will tell it to stop. So what do we know for sure that will tell our function to stop? Time. If the time is 0, then you should have $1,000. So if time equals 0, return $1,000. Okay, what if time is not 0? What if time is 12 months? And how do I find my balance? Well, we already kind of figured this out, right? To find the balance for the third month, I want the balance from the second month plus the balance from the second month times the interest rate. So how would this be different if I asked you for the balance of the 10th month? Balance of 9 plus balance of 9 times 0.01. All right, so in general, we just want to return balance it helps if you can spell correctly, balance of the previous month, so that's time minus 1, plus balance of the previous month times the interest rate. And yes, I know that 0.112 divided by 12 is 0.01. I left it this way so that if later on we wanted to change that where we allow the person to enter the interest rate, we would have a little variable right there instead. All right. I think that's it. I think that's all we need. Oops. Well, that one's still running, by the way. I got a negative number.
And then it got smaller.
And then it got smaller. So it's overloaded the size of int main, or integers. It's overloaded at this point. That's not good. So it's starting to give us garbage. We better kill that.
Now you should do it. Negative value, that's how you know they will start with it, right?
Yep. I think I just have to try running it again because I think it was because it was already running. That black box was already running. How many months do you want to invest your money for? I want to do it for a year. Do your taxes. Yeah, you're probably 1040 easy. Won't take long.
You're like 700.
All right. So here's the deal though. When you earn 12% interest compounded monthly, after 1 year, you didn't earn $120, you earn $126.83. So conversely, if that credit card company is charging you 15%, at the end of a year, you're not going to owe $1,150, you're actually going to owe more than that. That's right, 15% APR, that stands for annual percentage rate. So what that means is if they only charge you interest once a year, you would pay 15%. But they don't charge you interest once a year. So there's a different number called effective interest rate, which is actually higher, and that's what you're paying. You're actually paying the effective interest rate.
I thought you take the APR and divide it by 12.
No, that's worse than that because they charge interest on the interest on the interest. All right, you wanted me to run it again?
Some big interest rate probably not too big because eventually it's going to have a number.
How about 10 years? That would be 120 months.
Yeah. Now it's going to be slow. It has to go through.
It's slow because to compute the interest for the 27th month, it's got to compute the interest for months 1 through 26 first. It's got to recompute the interest every time it goes. So again, this recursive function is a very slow recursive function. Chris?
Could you make a new variable in the function that's just called the previous value? And then add that instead of calling your function again? Why not?
Yeah, I could. Or the better way to do it would be to not use a recursive function. Use the formula A equals P times 1 plus R over N to the NT. And that would run very quickly. So anyway, you can see recursive functions, when they have to run over and over and over again, can get very slow very fast. That sounds like an oxymoron. They can get very slow very fast. But this one is already very slow. We're only up to 28 months, which is a little more than 2 years, and it's already very slow, as you can see. But we already made $334.50. That's right. Woohoo. racking it up.
If you know
I don't
they
have
gave
that
us
kind of self.
12%,
Yeah, I would
what
say
if they
that.
gave us 1.2%?
All right, so you want to change it to 1.2%? But we're going to start with $1 million? For a year? Your $1 million turns into 1.2 million. I could, you know, I could live off that for a while. It'd be all right. Oh, you know what? It's not 1.2 million. This 1.2, that's the months. Because the numbers got too big, they ran into each other.
Yeah,
So that's 12 months.
You got 1,012.
You
or
get-
$1 million at 12.
You have 1012066. Yeah, you don't have 1.2 million dollars. Sorry, I lied to you. Darn months getting in the way.
Let us go through.
Yeah.